The final talk of the morning session before the break is by Prateek Sharma, who is going to follow up on this theme of cloud crushing with cooling, and hopefully we can get to the bottom of what cooling time is actually the important one. So please, Prateek.
So thanks a lot, Christoph and Drummond, for providing the background. So I'm actually going to talk about this recent work that was done by us at IISc, mainly by Vijit and Alankar, who are also in the audience. So I will really quickly go through the introduction, as most of it is already talked about. This question of where does multiphase gas, particularly the cold gas, come from is very, very important in variety of astrophysical objects, going from intracluster medium to cooling wakes of jellyfish galaxies to galactic outflows. And what is key, irrespective of the source of cold gas to begin with, the relative motion between the dense clouds and the diffuse medium. So there is relative motion between the two phases. And that's why idealized simulations like cloud crushing and turbulent shear layers. So Christoph talked about this, and Drummond talked about these are very, very useful to build up intuition as to what's going on. And the key takeaway actually for us is that the temperature distribution is broad, and the multiphase gas, even at the minimum of the cooling time, is long-lived. That means that turbulent mixing can keep up with this very short cooling time. So this is along the lines of what Drummond was saying. And this way, so if you have a broad temperature distribution, you can produce a range of ions as observed in a lot of observations. So here is sort of the cloud crushing setup. So I'll actually repeat very, very quickly what Drummond did for the shear problem. This is a very similar problem, but not the same, right? So the shear layer problem can be infinitely long-lived. You can reach a steady state, whereas in this problem there is no steady state. This is always transient. So this is one of the key differences. And the physical parameters for this problem can be sort of boiled down to these five: the density of the cloud, the temperature of the cloud, radius of the cloud, the density contrast ratio between the wind and the cloud, and the velocity of the wind, or more physically, the dimensionless parameters chi and the Mach number. These are very similar to what Drummond defined. Right, so basically turbulence, which is there in this problem without cooling, should also be quantified in terms of chi and Mach number globally, like Reynolds number, right? So these are like the dimensionless numbers of this problem. So there are important time scales for this problem, mainly the cloud crushing time, which is square root of chi times the crossing time, and the drag time, which is the time over which the hot wind pushes the cold cloud. And the key thing to notice is that the drag time is square root of chi times longer than the cloud crushing time. And the cloud crushing time is simply the Kelvin-Helmholtz time scale for the mixing of the dense cloud into the wind, right? So a key outcome of this problem, in absence of radiative cooling, is that the cloud, the dense cloud, is mixed before it can be pushed. So it is actually quite tricky to produce fast-moving cold gas in galactic outflows, for example, right? But when you put in cooling, there is a very, very important dimensionless number, which we already heard about from Drummond, this ratio of cooling time to the cloud crushing time, right? And the key question is, at what temperature should you calculate this cooling time? So these are the physical parameters, and there are also important numerical parameters which are going to be important, like the cloud resolution, like how many grid elements do you resolve the cloud radius by, the box size, and the boundary conditions. So this problem is, to my mind, so important that we have to pay attention to each and every small bit to really understand it well. And as you can see from the talks of Christoph and Drummond, that there are disagreements even in the basic background picture. So it's very important to pay attention to details. So if you do these simulations, in absence of cooling, all you do is you just mix this cloud with the wind. And even if you include magnetic fields, the picture does not change qualitatively, as Christoph said. Now, if we have, so this is a graph of dense mass defined as the density, total density in the box, including just gas with 1/3 of the cloud density as a function of time. So these dotted lines are simulations without cooling, and these solid lines are simulations with weak cooling. So as you increase the strength of cooling, or as you increase the size of your cloud, the clouds get dissipated for a little bit, but then at later times they start growing, which is shown here in blue and orange. So the picture changes qualitatively, right, in presence of cooling. And this was the fundamental contribution by Gronke and O in 2018, and similar results have been actually found by Lee et al. And Martin Spare and collaborators. So this is actually very, very important. And one of the reasons we sort of worked on it was there was a little bit of misunderstanding as to when does a cloud grow, and what is the condition for the growth of dense gas, basically. Right, so here, these are the typical parameters that we are using: chi of 100, Mach number of 1, and here we just vary the cloud size. So as you increase the cloud size, the clouds start to grow at late times. What about, so that was about the mass exchange between the two phases. What about momentum exchange? So here is mass in the dense phase. This is velocity difference between the cloud material and the wind material as a function of time, normalized to the drag time. And these have simulations without cooling and with cooling, and simulations where the cloud grows, that is where the dense gas grows. For example, here orange grows, right? Here the behavior of orange is very different from these lines, but here they are very, very similar. So what it means is that cooling does not affect the momentum transfer between the hot and the cold phases, and the cloud becomes co-moving with the diffuse wind over a time scale of over the T drag time scale. Here is actually a movie of number density for our high resolution cloud crushing simulations. So this will actually just show you visually what sort of structures we get. And so I'll play the movie, and I'll actually, I'll play the movie again. I'll actually pause it in the middle. So what you see here is, this is a movie from our very high resolution simulation with RCL by DCL of 64 and a box size which is smaller than what we think is an appropriate box size. But since this is high resolution, it actually shows a lot of details. So you see this, the cloud, the main body of the cloud being disrupted and mixed with the diffuse hot gas, producing a lot of gas at intermediate densities. After some time, this intermediate density gas cools very, very quickly. You see, so at this time, right, within the computational box, there isn't a lot of cold gas, but there is a lot of gas at the mixed temperature where the cooling time is very, very short. Okay, and so you start seeing the cooling of this mixed gas immediately after the dip that you see right here. So this dip represents the mixing phase, and this rise at later times shows this cooling of the mixed phase, which is responsible for the growth of this growth of the dense gas in these simulations. simulations. So here is a volume rendering movie of a snapshot of that simulation at a late time, at 14 cloud crushing times. And what we are sort of going through here is basically looking at these. So this is cooling time, and this is the transparency of this volume rendering image. So blue is material with very short cooling times, and red is material with longish cooling times. So as you can see, this tail has a lot of, has regions which are very cold and regions which are sort of hot. So cooler regions have short cooling times, and lower density, hotter regions have longer cooling times. So this is just a sort of walk through around this long extended tail at a fixed time. So you can actually see that the tail of this cloud is actually flared up, and there is a lot of low density gas there. Okay, so this shows this spaghetti-like, very fine structure of cold, turbulent gas. Okay, these surfaces are highly irregular, and gives a feel for this fractal nature of these cooling surfaces that Drummond talked about, and I think Max will talk about. Now let's look at some more quantitative diagnostics, like the probability distribution functions. This is this is fraction of volume occupied by the gas in our simulations as a function of temperature. And initially you have gas at 10 to the 4 and 10 to the 6 Kelvin. And because of this turbulence mixing layer, the intermediate temperature gas is populated. If there were no cooling, this low temperature peak would just move towards the high temperature, and it will become unimodal. But in presence of cooling, this cold dense peak builds up in time. So you have bimodal and very broad range of temperatures in your simulations. This is a volume distribution of pressure, and what you see here is, the initial condition was isobaric, but with time you actually develop a low pressure tail. And this is something Drummond was sort of mentioning, that this may be a numerical artifact, but we have actually checked it with our simulations with RCL by D cell of 8 going till 64, and we see these PDF to be very, very similar. There isn't much change. The other thing that you notice here is that at late times, the ambient medium itself can cool. So this is not the regime that we are interested in. We are interested in the cooling of the mixed gas. But physically, this can also be very, very important, because for example, in galaxy clusters, the ambient gas can have non-negligible cooling time. So, but this problem is even harder in some sense. It's not as idealized. So you have to worry about the ICM thermodynamics, for example. What about the cooling time? So this is a plot of cooling time as a function of temperature, right? And this green, so focus on this green dash line and this 1 sigma spread. So what we are plotting here is the cooling time, 3/2 nkt over n squared lambda, at all the points in our simulations. Okay, so we see that it sort of follows this curve, and then we want to see, so in addition to that, these simulation data points, we include in red here the isobaric cooling time, which is this. So basically you assume the pressure to be constant across all temperatures. So the red line shows the isobaric cooling time, and the blue here shows the isochoric cooling time, where you assume that the density across these temperature range is held fixed. And you can actually clearly see that the simulation points agree very well with the isobaric cooling time. Okay, so our tail, the cooling tail, is close to isobaric, but not perfectly isobaric, because we saw those tails in the pressure PDF. Now, this is actually an interesting plot that is sort of somewhat directly connected to observables. What I'm plotting here is the differential emission measure. So luminosity coming out at a given temperature bin as a function of temperature. So this is E dot. So these are from our simulations. These are PDFs from our simulations. And what you see is that there is a lot of emission coming out across a range of temperatures, right? So the differential emission measure is pretty flat. Whereas if we just do a simple cooling flow model saying that the gas from the hot phase comes and cools to the cold phase because of just cooling, as in a simple cooling flow, these are the arguments that you make, right? E dot cool is nothing but thermal energy content divided by the cooling time. So this is the rate at which plasma emits and moves in these temperature bins. Similarly, m dot cool is simply the mass of the gas at a given temperature bin divided by the cooling time. And if you take the ratio of these two, you get E dot cool, which is proportional to m dot and is proportional to temperature. So this is the prediction for this differential emission measure as a function of temperature. So this y-axis should go like, should be proportional to T, as shown here in this dashed line in black. And so this is sort of, this is the precise number if you scale with the typical m dots for the cold gas that we see. What is seen here is that you're suppressing emission at 10 to the 5, 10 to the 5.5 Kelvin, but exceeding it at 10 to the 4, 4.5 Kelvin, right? So this is a fundamental, so I argue that this is a fundamental property of turbulent cooling, turbulent flows where radiative cooling is important, right? And this mass flow is not a simple simple steady cooling flow. There is a lot of mass flow because of turbulence across these temperature bins. So this feature of broad temperature distribution of emission may explain the variety of observed ions that we see. Okay, and this is not the only place where we see it.
4 minutes, Prateek, sorry.
Okay, so these are some older simulations in the context of galaxy, cool core clusters of galaxies, and this is exactly the same quantity, the differential emission measure as a function of temperature. And what you see are these DEMs from these simulations, and what you see is this broad distribution of temperatures in the emission, right? And even for a simple cooling flow, which is multi-phase, it differs from this simple cooling flow, steady cooling flow model. And this is a plot from Neer's recent paper on interaction of filaments with the ambient medium. And here also you see like an inverted slope of this rather than a positive slope predicted by a steady cooling flow driven just by cooling. So turbulence fundamentally changes the nature of these emission signatures and the physics of these boundary layers. Now, so this is sort of the last few minutes of my talk. I'll talk about this discrepancy that has cropped up in the threshold radius for the growth of clouds. So Max, Gronke, and Pango's group have argued that it's the ratio of the cooling time of the mixed phase and the cloud crushing time which determines the threshold radius for the cloud growth, whereas other groups, for example Lee and Hopkins group at Caltech, and also Martin, Spare, and Christoph were arguing for the hot gas cooling time to be important. And if we just plug in their formulae in terms of these important physical parameters, these are the numbers that we get. And here I plot the ratio of the Gronke-O radius to the Lee et al. Radius in the Mach number chi space. And you see that the Gronke-O radius for the threshold radius for the cloud growth is 100 times smaller, even for a density contrast of 200. So that means this is actually a big discrepancy in terms of whether dense gas grows or not. Now, we have actually carried out extensive simulations specifically trying to resolve this discrepancy. So we have, so these are the possible reasons. So see, the physics apart, these are almost identical simulations, right? And how can one group doing exactly the same simulations get an answer which is just an experiment, and you measure this in your numerical experiment, get a different answer? That's the puzzle. Physical reason can be different. So this is the mystery. So both criteria based on similar numerical simulations get a different threshold radius, and this threshold radius can differ by orders of magnitude. And these are the possible reasons. And the main ones are the box size and what do we mean by cloud destruction. So here we actually show our simulations data on the same. So this dashed line on this parameter space delineates the region where you have growth versus destruction, and these solid lines are predictions from Gronke-O model, and this is from Lee et al. Type criteria, and we see growth at these intermediate radii. That means we see growth of dense gas for smaller radii, and we are somewhat in agreement with this, but not exactly, because we do not see cloud growth for somewhat larger radii than the Gronke-O radius. So there are like some disagreements, but the main picture that sort of emerges. So I'm actually going to skip over the details, but the main reason for this discrepancy is the box size and defining what is meant by cloud destruction. Okay, so I will. So this shows that the small box size reduces cloud growth because the mixed gas moves out of the box. Okay, but this box size is not enough to explain the full discrepancy. Similarly, there are effects of resolution, and in fact, what we see is with increasing resolution, we do not see convergence even in this dense mass as a function of time, right? If they were converged in a volume sense, these all should have approached each other, but we don't see that. Now, so when we were trying to finish up our paper, Martin and Christoph had their paper, and they do have bigger box sizes. And what we find is that it's very important to pay attention to how you define what is meant by growth or destruction of dense gas. If you run your simulation, if you don't run your simulation long enough, for example, this run from their paper, you will sort of conclude that this cloud is destroyed. But at later times, it actually grows. And I thank Martin for running this for longer and sort of checking it. So basically, it's important to pay attention to what you mean by growth. And so we propose a robust definition, and the robust definition is that you should run for a significant fraction of the cooling time of the hot phase and see if the dense mass grows after a dip. And this corresponds to cooling of the turbulent boundary layer and not the background hot phase, so it's very important. Okay, so here are my concluding thoughts. We have cloud tail with a broad temperature distribution and a broad differential emission measure PDF. It's not a simple cooling flow. It's qualitatively different. We think that we have resolved this apparent discrepancy between numerical results of different groups, and I think the key culprit is the definition of what you mean by cloud growth in the cloud crushing problem. So it's the cooling of the mixed gas, which we find in our numerical experiments, determines cloud growth. More simulations are needed to precisely map out the growth threshold. For example, things like whether it's the square root of the temperature or whether it's the minimum it's the temperature at which the cooling time is minimum. What is more important to define your T-cool mix? This we have not figured out. And of course, there are a lot of other issues, open issues. For example, where does the cold gas come from in the first place? And how do we stop dense mass growth in outflows, about which Evan will talk tomorrow, I think. Thank you. And I actually end with the quote by Donald Lindenbell. And in fact, he just, we were just talking, and he just said that about something on reconnection. Let's learn to walk before we can run. So, this interplay of cooling and mixing is not a trivial problem, and we should be very, very careful as we tread ahead. With that, I thank you all for your attention.
Thank you very much, Prateek, especially for those concluding, for that dire warning to us all in your concluding thoughts. Appreciate that. I'll let Christoph ask the first question.
Thanks a lot, Prateek. Very nice talk. I appreciate it very much. So I think we completely agree with your conclusion that the definition of growth matters whether you are finding yourself in the growing or in this destruction regime. And I would argue, in fact, with Martin together, we discussed this at length. And in the end, we concluded that there's no unique definition. And I think it really matters which problem you want to understand. If you want to understand jellyfish galaxies, or if you want to understand mass loading, then I think you can't wait forever until you lose 90% of your mass and then have a slight mass growth in the end. We would then argue actually looking at a time scale a little bit earlier, because you want to connect these tails to these blobs basically. But I completely agree that the outcome depends on the definition, and we would argue it really depends on the problem at hand, and there will be no unique definition that suits all possible problems you can imagine here.
Right. I agree with you, but here we are sort of taking a physicist's viewpoint, saying that this is a well-defined problem, until when I think, as we showed, that whether you get growth or not, a threshold radius can differ by a factor of 100 or more, and that's actually a big discrepancy. So you better, we better be clear about what do we mean actually. That's all I'm saying. You're right that if the jellyfish galaxy grows in, say, 10 gigayears, which is comparable to the Hubble time, then you should not wait for such a long time. So I totally agree with that. Yeah.
So I think the insight is going to high density ratios will reveal itself basically, because there the difference is largest. And yes, studying actually the regime of a density contrast of 1,000 or even more is, I think, the key to go for, because that is which basically is the relevant part, I would say.
Mm-hmm. That's where the difference is the biggest. Yeah.
Yeah.
So let me ask a question, Prateek. I was just a little puzzled by, you showed the plot of the velocity of the cold cloud, and you basically showed that the velocity decreases the same rate irrespective of what the mass in entrainment was, irrespective of the cooling time. Do you understand that, given that the interpretation of mass exchange leading to momentum exchange, kind of what we heard from Drummond earlier? So how can you get similar exchanges of momentum with such different exchanges of mass?
Right. So so I mean, this is what we get in simulations. That's the first thing. The other thing is, if the dense gas, if the gas is sort of coming and sort of condensing from the hot phase, then it will also accrete momentum of the hot phase, and that's so basically it's a competition between mass accretion, and this mass, it really depends on the velocity of this mass that comes and accretes onto the tail. And I actually have to say that I haven't really analyzed this as much as I should, in the sense of how to make sense of it, but this is what we get. In fact, we did the same plot so this was based on tracer, but we did the same plot with temperature. So we just sort of cold and hot, and we don't see a substantially different result. So this is the same plot, but done with, so these are two sets of radii, and this is for the for our fiducial simulation, one is based on temperature, the other is on tracer, and delta V is almost very, very similar. Here there is a little difference when the cloud size is smaller, but still, the time scale I would say is very similar.
Okay, so the plot you were showing before was tracer based, you were saying?
Yes, that's correct.
Okay, thanks.
This was based on tracer.
Thanks. Frank van den Bosch had a question.
Thanks. I'm trying to understand something, and it relates also to Drummond's talk. So if the relevant time here is the cooling time of the mixed material, then ultimately it's set by the rate at which material mixes, and we reach that intermediate temperature. And it seems to me that must depend on the inertial range, the effective inertial range of the turbulence. In other words, the ratio between the larger scale on which you drive the eddies and the scale at which they dissipate. And the latter is depending on numerics, on your resolution. So I would expect, therefore, in other words, if that is true, and that rate is ultimately set by then basically means that the effective resolution that you need to read in order to really resolve would be the actual Kolmogorov scale, the real physical scale. So what? It wasn't clear whether you and or Drummond agree with that statement.
Right. So let me actually make an analogy with turbulence simulations in absence of cooling. Right. When people do simulations of turbulence, and if they don't explicitly include viscosity, right, they get a bigger and bigger inertial scale with higher and higher resolution. Right. Does that mean that this is converged or not converged? So in the sense of large scale properties, in the sense of global properties, including having a higher resolution just increases your Reynolds number, right? And if you just increase your Reynolds number, the property of the turbulent flow is very, very similar, except that you have more details in small scales, right? So
except that Drummond made the argument that it depends on the area, okay, the area of the mixing layer, and the area of the mixing layer increases when you go to when your inertial range of the turbulence that you resolve gets larger, and that's how this resolution would come in and would matter.
Right. So I think I would leave that question for Drummond to answer, because here I have really I've just done numerical experiments. I think the problem of turbulence is hard, and I would just try to do experiments and understand them first before building a sophisticated theory. So I would actually let Drummond answer that.
Drummond, if you can answer that in less than a minute and a half, go for it. Otherwise, let's do it in the discussion.
I think that sounds good.
Yeah, I'll very, very quickly, I'll just say, I don't agree with that. That's something that we've grappled with a lot. And I think, there's a lot of different moving pieces here, but essentially the fundamental point is that your, Kolmogorov turbulence says that the energy flux on any given scale is the same, right? So you have the same energy on each eddy scale. And so as long as you're sort of loading the first eddy with the same amount of temperature, which is due to resolving the largest scale eddies, that is going to flow down the turbulent cascade. And I completely agree, Frank, that when you increase the cell size, and you will therefore sort of truncate the turbulent cascade earlier, you will decrease the area, but you also thicken the cell, and so thicken the layer. And so what we find is that the total volume of cooling, this product of the area times the width, remains constant with resolution. And this is a result of the fact that really what it boils down to is that both turbulence and numerical resolution have a Prandtl number of 1. And so you are mixing the momentum and the temperature at the same rate. But that's more than 90 seconds. We can talk more on this.
We can, let's pick that up again in the discussion. So thank you again to Prateek, and thank you to all of our speakers this morning.